Welcome to Chem We Talk, a channel where we're not afraid to talk about any chemistry topic. In today's video, we will discuss the difference between strong and weak acids, including some pH calculations involving those species. Before we get started, let's just take a look at the questions that we're going to try to answer today, such as what is a Bronsted-Lowry acid-base theory, what is a pH, what is the difference between strong and weak acids, and how do we calculate pH of solutions containing either strong or weak acid, and what is percent ionization. There's a different video in this channel that goes over all the different acid-base theories, but for today's video, we're only going to focus on the Bronsted-Lowry one. So for Bronsted-Lowry, an acid is any species that can donate an H+, and a base is any species that can accept that H+. So let's use the hydrochloric HCl example in water. So HCl can donate its hydrogen to H2O, which means HCl behaves as an acid and H2O as a base, producing H3O+ and Cl-. In principle, H3O+ could donate its hydrogen to Cl-, behave as an acid, and Cl- would take that hydrogen and would behave as a base. So we say that Cl- is the conjugate base of HCl. Okay, so when we're discussing the difference between strong and weak acids, what's going to determine that? It's going to be the ability of the acids to donate its H+. We're going to go much more in depth than that in a second. Okay, so we're going to use the pH scale to measure the acidity. And that scale is just used to represent the concentration of H+ and H3O+ in a system. And let's just look at some notation here for a second. The brackets just means concentration in molarity, and H+ and H3O+ would be used interchangeably in this lecture. Okay, so P in chemistry just means negative log of anything. So we'll discuss later on about pKa, pKws, pKbs, pKsbs even. And those just means negative log of whatever follows it. So in the case of pH, whatever follows the letter P is H. So pH just simply means negative log of H+ or H3O+ concentration, where again, the concentration of H+ will be represented in molarity. Okay, so let's look at two examples here. The first one is, what is the pH of solution that contains 0.01 molar H3O+? So if this is the concentration of H3O+, let's just plug it into the equation and we get negative log of 0.01 equals 2. And that is because if you move the negative sign to this side here, that's going to come log of 0.01 equals -2. And we know that because this is a log base 10, we have 10 raised to -2 equals 0.01. That's where it comes from. Okay, so let's look at a different example using slightly smaller concentration, 0.001 molar now. And let's do the same calculation. And we note that now the pH, if I plug it in the concentration into it, becomes 3. So let's take a look at those concentrations. Going from here to here, I'm increasing my concentration by 10. And from here to here, my pH decreased by 1 unit. So the change in concentration is much more drastically than the change in pH. And we're going to discuss about that in a second. Okay, so one thing that we need to ask ourselves is, why do we use a pH scale? Why would someone bother take the negative log of something? And the reason is, let's take a look at this example, so see if we can figure that out. We have H3O+ that has a concentration of 0.000, I'm lost count of it already. I think there are 9 zeros there. So the molarity is 1 times 10⁻10 molar. So if I would calculate the pH for the solution, plug it in there, my pH would be 10. So it is much easier to say that the pH equals 10 than to say that the concentration of H3O+ is 0.00090 zeros with a 1 at the end. Okay, so that's just for convenience. It's easier to use the pH notation. Okay, some things to remember. Because of the negative sign of the pH, the lower the pH, the more acidic the solution. So the more H3O+ you have, the more acidic the solution will be. And another thing that you need to notice that because we are dealing with a base 10 scale, a log scale, it's not like linear. For example, if I look at gastric acid and lemon juice here, the change in pH is only by 1, but the change in concentration is by 10. So lemon juice has 10 times less H+ than gastric acid. Okay, so let's look at the strong acids for a second, and I'm going to show you later how do you calculate the pH for strong acid. But let's just assume for now that we already know that those are strong acids. And let's use Bronsted-Lowry. HCl will donate its hydrogen, produce H3O+ and Cl-. Same thing with HNO3, producing H3O+ and NO3-. Just pay attention now to this H2SO4. You might feel tempted to take out 2 of those hydrogens, but it turns out that H2SO4 will only easily lose its first hydrogen, And it kind of makes sense, right? Because after you remove the first hydrogen, you produce HSO4-, which is a negatively charged species. So if you want to take a positively charged H plus from something that is already negative, it's going to be much harder than the first one, right? So this is going to be a topic for a different video when we discuss polyprotic acids. But just know that the H2SO4 is going to be a strong acid. But going back to those two that are monoprotic, the conjugate base of those strong acids will be spectator ions because this reaction only goes in one direction from left to right. There's no way the HCl- will react with H3O plus to go back to HCl. Okay, so let's take a look at this hypothetical scenario. I have a solution with 0.1 molar HCl at time equals 0. If I drop there, leave that sitting for 5 minutes and come back, how many moles, or what's the concentration, if I were to ask, of HCl, like HCl is a whole molecule, H bonded, covalently bonded to Cl, would I see after 5 minutes? The answer is actually 0, right? We just said that HCl will break apart completely to produce H3O plus and Cl minus. So all this 0.1 molar, that 0.1 moles that was in this 1 liter solution will be converted to H3O plus and Cl minus. All right, so how do you calculate pH for strong acids? Let's use that solution again as an example. So if I have a 0.1 molar HCl solution, let's see what happens. So I'm just representing here two different types of methods. People usually show those in lectures or exams. In one way, we write water as being part of the reaction. The other one, we just ignore the water and split the ions. But they behave the same way. So we have HCl being 0.1 molar. After I leave there for a second, it's going to break apart into H3O plus and Cl minus. So the total concentration of H3O plus solution will be 0.1. So if you need to calculate the pH, we just need to take the negative log of 0.1, which is going to be 1. So the pH of the solution is 1. And for strong acids, very simple. The final H3O plus concentration is simply equal to the initial acid concentration. Let's just give you some tips now on how to memorize your 7 strong acids. So they can be broken into 2 categories, hydroacids and oxyacids. The hydroacids, they do not contain oxygen, while the oxyacids have oxygen on it. Okay, so for the hydroacid, the strong ones are simply the hydroacids that contain halogen atoms, which means they are from group 17, with the exception of HF, which is the first one. That's going to be a weak acid. For the oxyacids, there is more of a mathematical way to kind of predict if an acid is going to be strong or not. They are represented by this general HXMOY formula, where X denotes the number of hydrogens present and the Y denotes the number of oxygens present. And the larger the Y minus X, so the difference between the number of oxygens and hydrogens, the stronger will the acid be. Okay? And then when this difference is equal or greater than 2, generally you're going to get a strong acid. So let's take a look at our examples here of strong acids. So oxygen, we have 3 here for HNO3 and 1 hydrogen, so 3 minus 1 gives you 2. So if it is 2 or greater, it's a strong acid. 4 minus 1 gives you 3, strong acid. 3 minus 1 gives you 2, so strong acid. And then 4 minus 2 gives you a strong acid. And just to be careful with H2SO4 because it's a polyprotic acid. And in that case, only the first hydrogen is considered a strong acid. So removing the first one makes it a strong acid, while the second one will be a weaker acid. All right, so we already can note for the weak acids that there's a difference. Now we don't have a single arrow anymore, but we have a double arrow. And what does that mean is we get a equilibrium. So, but the reaction is going to proceed the same way first. So the acid is going to donate its hydrogen, producing H3O plus and F minus. And H4 plus, which is a weak acid, is going to donate its hydrogen, producing H3O plus and H3. And HA is just going to be a representation for any monoprotic weak acid. And by monoprotic, we means that only has 1 hydrogen. Okay, so H3O plus plus A minus. And now those weak bases are not spectator anymore because they come from weak species. So those conjugate bases will actually be weak bases and will not be spectator. Okay, so let's do the same type of scenario. We have a 0.1 molar solution of HA at t equals 0 minute. We let that sit there for 5 minutes, and now I come back and ask you, how many moles, or what is the concentration of HA, like combined H bonded covalent with an A, that will be present after 5 minutes? So differently than the HCl case, which was a strong acid, the answer is will not be 0. There will still be some HA present. But now the question is, how do we calculate how much HA will be present? Okay, so let's look at this example. We have the same acetic acid solution, which is a monoprotic acid that is also 0.1 molar. Okay, anytime there is a question about weak acids and asking for pH, the first thing you need to ask is what is the Ka, just basically the equilibrium constant for the dissociation or ionization of a weak acid. Okay, so every time you have a weak acid, write down the reaction. And you know this should be an equilibrium arrow, not a single arrow. And if it is an equilibrium reaction, you need to write a nice table, okay? And we know that a Ka equals to the concentration at equilibrium of your base, conjugate base, times the concentration of H3O plus divided by the concentration of your acid at equilibrium. So if you're looking for equilibrium, we need to draw a nice table. Okay, so let's see what the problem gives us. And if you remember correctly, for ice tables, we cannot include any liquids or solids. So H2O that's liquid, we'll just ignore for our calculations. And what is given to us that we have a 0.1 molar solution, so we plug that in. And nothing else was mentioned, so we're just going to assume that it's 0 and 0 for A minus H3O plus. Then in the C row, which is called the change row, I also like to call it the coefficient row. So if it is a reactant, you're just going to put a negative sign. If it is a product, you're going to put a positive sign. And then just going to put x according to the coefficients. In this case, we have 1, 1, 1, 1. So just going to be minus x and plus x. And then the last row, we just read the first two rows together. So it will be 0.1 minus x, 0 plus x, 0 plus x, and you end up with this. And we were given Ka, right? So we can just plug it in. What we have here in our table, so we know that should be the A minus at equilibrium, which corresponds to this value, H3O plus at equilibrium, which corresponds to x, so we get x times x, and then the HA at equilibrium would be the 0.1 minus x, which is coming from this part. Okay, so you get x squared, x times x squared, get 0.1 minus x equals to the Ka value. We're going to assume that this x is negligible, but in the next slide we're going to show you when we are sure that this assumption can be made. If we do that, we get x squared equals to 1.8 times 10 to the negative 5 times this 0.1, right? If I multiply 0.1 by this, which gives me x squared equals 1.8 times 10 to the negative 6. If I just take the square root on both sides, I end up with x equals 0.0013 molar. And if we go back to our table, x corresponds to H3O plus concentration at equilibrium, right? So if we know the H3O plus concentration, we can calculate the pH. So simply take the negative log of x here in our table, which is going to be 2.87. So if you remember, for HCl it was 1, now it is 2.87 for the same concentration. All right, but let's check our assumption. So what I did here, I just plugged in everything back into the table, substituting x. So we have the 0.0013, and then we get 0.0987 molar here, which is how much of your acid was left. So remember when I asked how many moles or what was the concentration of HA left in the flask, it turns out it was 0.09. So almost everything remained is HA. So only a tiny amount broke apart. Okay. So generally, this x we're going to be considered negligible when we get the x that we get from that expression and divide it by the initial concentration of your acid and multiply by 100. If that is less than 5%, we should be good. So let's do it in our case. Get 0.0013 molar, which is this, divided by 0.1 times 100, and we get 1.3%. So we're good. So this assumption holds. But in the case where that doesn't happen, we need to use the quadratic equation. All right, so let's compare, put side by side a strong and a weak acid. So let's start with the strong acid first, using the 0.1 molar. We saw that the pH was simply the negative log of 0.1 molar, which gave rise to a pH of 1. For a weak acid, the situation was a little bit more complicated because we need to draw an ice table, find SO for X using Ka, and then you could find the pH, so you got a 2.87. But if I ask you now, what is called the percent ionization for this reaction? And percent ionization, which is represented by alpha, just means how much of your acid broke apart to produce H3O+. So for a strong acid, we assume that all the HCl breaks apart to produce H3O+ and Cl-. So at the end, if I were to calculate, we are saying that if I start with 0.1 molar HCl, all of it will break apart, producing 0.1 molar H3O plus, and when we multiply by 100, we get 100% ionization. In the case of a weak acid, let's do the same procedure. Our initial concentration of acid was exactly the same as for the strong acid, which was 0.1, but our final H3O plus concentration was slightly different, right? Now we get 0.0013 rather than 0.1. It's actually like very pronounced difference. And when we multiply that by 100, we get a 1.3%. What does that mean is that for every 100 HA molecules, only 1.3 of it will break apart, producing H plus and A minus. Okay, so the strong acid and weak acid, they differ by what's called the percent ionization. For the same acid concentration, like in the example, they were both 0.1, the strong acid will have a much lower pH. Okay, let's just do a quick summary. pH scale is used to measure the level of acidity of a solution. The P just means the negative log of something, and in our case, of pH, P is going to mean the negative log of H3O plus concentration, or H plus, because those can be used interchangeably. Okay, the lower the pH, the more acidic the solution, and because pH is not a linear scale, a change in 1 unit of pH corresponds to a 10-fold change in concentration. So if you change the pH by 2, you're going to be changing the concentration by 100 times. Okay, strong acids ionize completely. So for calculating the pH of them, simply take the negative log of the initial acid concentration, and you can find the pH right away. For weak acids, because they do not ionize completely, you need to set up a nice table and use Ka to find X and then take the negative log of it. So just be careful when doing those calculations. You need to check if you're making your X negligible in your calculation. When alpha, whether your percent ionization is less than 5%, you should be good to go. Other than that, you need to use the quadratic equation. All right. Thank you so much for watching. Hope you enjoyed. If it was helpful, please feel free to share with your friends, colleagues, and lab mates, and follow us on the social media. All right. Bye. Thank you.